Greetings. It's been a hot minute. Welcome back. If you're kind of following along as I'm actively uploading these videos, it has been a while since I've last uploaded one on anything AP Physics C related. This is the first video in a series on the electricity and magnetism portion of AP Physics C, where in this first unit we are covering mostly electric forces and fields. So in this first chapter, I'm going to cover the electrostatic force, or the Coulomb force, depending on how you like to label it, which is basically characterizing the mutual force that charges tend to exert on each other, whether it be attractive or repulsive. All right. So the main equation that we're going to be taking a look at in this video is Coulomb's law, and this is the equation that really started it all. This is an equation that was experimentally derived by Charles-Augustin de Coulomb, meaning it helped form much of the theoretical foundation of electrostatics. It states that for any two objects with a net charge, those objects will exert equal and opposite forces on each other, according to this equation right here. Now, you'll note that this equation looks oddly similar to another equation for a certain force covered in mechanics. And it's no coincidence either. Both gravity and electric force both are considered field forces, which tend to fall off sharply with distance. We will get into more detail about what I mean by fields later, but for now, just know that Coulomb didn't just copy Newton. Sometimes physics just has funny happenstances like that. Now, this equation multiplies a constant value k, known as Coulomb's constant, by the product of the magnitude of the net charge held by two charges, 1 and 2, before being divided by the distance between them squared. Now, I make it a point to express this equation in terms of as many absolute value brackets as possible, because the inclusion of positive and negative charge within electrostatics as a concept often leads to mix-ups with our usual convention of left and right being negative and positive, respectively. This means it's especially important to draw free body diagrams for electrostatics problems, so that's something I'll emphasize again later. Now, speaking of positive and negative charges, we have a very important set of rules that are unique to electric force. So first, if you have two charges of similar signs, such as two protons, which are both of positive charge, they will always exert a repulsive force on each other, meaning that they will push each other away, always. If the two charges instead have opposite sign, such as a proton and an electron, the electric force will instead be attractive. So each charge will pull the other toward itself. This rule set is important to understand well because it heavily influences the direction of the forces that you'll be calculating throughout this unit. So keep it in mind. Now, I'd like to get into some of the finer details. First off, any charge Q is expressed in units of coulombs, named after the guy who made enough slam dunk developments in the field to deserve that honor. It's worth noting that coulombs are a derived unit, kind of similar to newtons and joules. In terms of actual base units, a coulomb would be expressed in ampere seconds, which is a unit where amperes, I guess, are a unit that we'll use later to describe the flow of charge in circuits and stuff. Now, within Coulomb's law, that mysterious constant K, I figure deserves some elaboration. The Coulomb constant K is defined as 1 over 4 pi epsilon naught, or I guess more practically, it is 9 times 10 to the 9 Newton meters squared divided by Coulomb squared. This is a pretty nice, easy constant to remember, 9e9. And it's important to remember it well because you do end up using it a lot in electrostatics, as you'll find out later. Now, you might be wondering what on earth that epsilon naught is. That value is known as the vacuum permittivity, or I like to call it the permittivity of free space. It's a constant that, while not very important for the time being, is very important for several applications later on, including a pretty important set of equations and derivations that helped to revolutionize physics. Now, for your convenience, both of those quantities are included on the AP Physics formula sheet, so there's really no need to memorize them. Now, I would say, for the sake of efficiency, I would recommend at least having familiarity with Coulomb's constant. That's, again, mostly because, for the sake of time, it's nice if you don't have to reference that constant, which you'll be using a lot. Finally, I would like to go through some general tips and tricks that I feel like you should know. First, I'd say a common mistake that I see is that people will accidentally blow the net force on a charge out of proportion because the charges exert mutual forces on each other. So the misunderstanding is that because the charges are exerting mutual forces, you kind of think that there's actually double the force that you'd normally be calculating with this equation, because they're both, going towards each other simultaneously, or both going away simultaneously. It's important to recognize that each charge only exerts a single force on the other, given by Coulomb's law. So, for example, I would say something like charge 1 is going to exert a singular force on charge 2. So the net force acting on charge 2 is really just that one force. There's nothing more to it. Another thing is the labeling convention that I like to use for electric force. Because we're sometimes going to be dealing with multiple charges exerting forces on each other, as you'll see later, I like to use the double subscript labeling convention. Again, using a hypothetical charge 1 and charge 2 as an example, the force that charge 1 exerts on charge 2 would be labeled as F12. So I guess conversely, the force that charge 2 exerts on charge 1 would be labeled as F21. This convention is really just going to help better distinguish equal and opposite force pairs, which differ in direction and also help with simplifying things through symmetry. Finally, I cannot stress enough the importance of drawing a free body diagram. It's really easy to get caught up in mistakes involving direction with electrostatics. So the more you can do to kind of orient yourself and keep track of direction, the better. With all of that in mind, I'm going to cover a couple of examples that make use of Coulomb's law and how to work with it. And hopefully through that, you should get the gist of how to work with this stuff and, blast through the tedium of applying it. So let's see what we got. All right. So before we head into slightly more abstract examples that involve point particles, I figured I'd give you an example that shows how electrostatics works on a more tabletop realm. Here we've got two balloons that are separated by some mysterious magical distance, where both balloons are suspended by strings, both of equal length, as given here. Both of these balloons have been given some mysterious charge Q that we're going to end up finding in this problem. And we're going to assume that it's the same for both balloons. Now, both of these balloons are at equilibrium, which means this is effectively a static equilibrium problem. The forces are all going to add to 0. And we are given the distance from the center of one balloon to the other. So we'll go ahead and mark that distance on here just for our own convenience. That the center of the center distance, which all, draws a little curly bracket or something, labeled as R, is going to be 0.5 meters. Now, here we have the length L, we have some mysterious angle theta that we'll probably need to find because it's not given in the text of the problem. And then we have the mass of the balloons. And that's basically it. With that information in hand, we are supposed to find the charge Q as well as how many excess electrons each balloon has. Interesting. So the first thing we're going to note right off the bat, just to establish the type of problem that this is that, again, this is in static equilibrium. So we can say that the sum of forces is going to equal 0. That is, that the sum of the forces in both directions, x and y, are both going to add to 0. Now, because this is a force-related problem, as always, it is very important to draw a free body diagram. Now, it does say that we're supposed to draw free body diagrams for each balloon. I'm only going to do one, and I'll explain why after we do the first balloon. So over here, first off, we have a mass, and because these balloons have mass, you can always draw a force due to gravity acting straight downwards on this balloon right here. I'll prioritize the left one. So this is going to be force of gravity, like usual. Now, the balloons are suspended from a string, so there is also going to be a force of tension acting on each balloon, which I'm going to denote with a green force vector going up and to the right for this leftward balloon right here. We'll call that T. And then finally, we have the star of the show for this unit, which is electrostatic force, and I'm going to denote that with blue for this case. Now, it's important to note that both of these balloons, we were told, have the same charge, and we're going to assume that they have the same sign of charge as well. Remember that if two objects that are charged have like sign, they are going to repel each other. That means that the force that this balloon right here exerts on our leftward balloon is going to be a repulsive force. It's going to push this balloon away from itself. That means that our electrostatic force on this leftward balloon is going to act to the left in this case. And we'll denote that with F sub E. And that is basically our free body diagram. The last thing we could really do here is maybe to split this angled tension into components, because something needs to account for this net force that we've got from these other two forces down here. So I'll go ahead and do that, and then I'll label this as Ty and Tx, respectively. Now, I'm really only going to draw this free body diagram. And the reason why is because the free body diagram for this rightward balloon is effectively going to be the same thing. The only difference is it's going to be a mirror image of this free body diagram. So instead of the tension going up and to the right, it's going to go up and to the left. The electrostatic force from this balloon on the rightward balloon is also going to be a repulsive force. The only difference is that because it's trying to push the rightward balloon away from itself, the electrostatic force is going to act to the right over here. Again, the forces, or the electrostatic force between two charges, is always going to be equal and opposite. Now, with that in mind, I'm going to save some time by not doing that. So just know in the future, sometimes you can save some time with symmetry, because a lot of these things in electrostatics are going to be matched equally and oppositely. Now, the last thing here is that we do have this mysterious angle that we'll eventually need to worry about. Now, over here, I will say that we do have some measurements that will allow us to find that angle. So when we need to, we can take advantage of that. For example, we do know the length of the string. So if we were to draw a right triangle made with the hypotenuse, seemingly, the vertical, and then, half of the separation distance between these balloons, well, the length L is a length 1.5 meters over here. This is the angle that everything is given with respect to. This is our right angle on our right triangle. And then it's worth keeping in mind that the base of this right triangle is not going to be 0.5 because that makes the full non-right triangle. Instead, it's going to be half of that. So this base of this right triangle will be 0.25 meters. Now, I'm going to leave it at that for now. We'll worry about it when we need to, but for now, let's just go ahead and keep that in mind for later. Now back to our forces thing. So our goal, again, is to figure out the unknown charge Q on this balloon. So we're just going to kind of set things up as if it were a force problem, and eventually our unknown should rear its head, probably with Coulomb's law. So over here, obviously, since we're splitting things up into components, we should go ahead and split the sum of forces into the sum of forces in the x direction equaling 0. And over here, kind of off to the side, the sum of forces in the y direction also equaling 0. Now, anytime that you have an unknown and you're not sure which direction to go with, I would say it's generally good practice just to kind of work both simultaneously. And if you hit a roadblock at some point along the way, work the other direction, and you will generally find your way out. So I'm going to start with the x first, because it does involve our star of the show. And in this direction, it seems like we have a rightward component of tension counteracted by a leftward component due to the electrostatic force. So over here, I'm going to color code things for the first line, and then I'll switch to white after that. But we have a rightward component, Tx, that must equal the electrostatic force in the opposite direction. I would probably expand out the sum of forces first before setting things equal to each other, but here, because it's only those two forces, they have to equal each other. There's no other way around it. Now, on the other side of things, we have a vertical component of tension, Ty, counteracted by gravity in the opposite direction. And again, it's only two forces, so they must equal each other. No way around it. So these forces can stand to be expanded out. We have equations for a lot of them. For example, the x component of tension is going to involve some trig. This is the angle we've got within the triangle. So if we want to find Tx relative to this overall tension, T, which is shared between both equations, it's going to be the opposite side relative to this angle. So down here, we can write this out or expand it out as T. I'll go ahead and switch to a base color. We can expand this out to T times sine of our unknown theta, equaling the star of the show, the electrostatic force, which I will write as K times Q1 times Q2. But here, because both balloons are assumed to have the same charge, Q1 times Q2 will effectively be Q times Q, which we can write as Q squared in this case. And then we're going to divide that by the distance between them squared, which in this case is R squared. So that's our equation there. Now the problem is we don't know what this tension is right here. We need to figure that out. And so because of that, we're not exactly able to solve for big Q yet. We're going to have to switch directions and see if we can get a way in. So I'm going to switch over here and we're going to do the same thing. We're going to expand out Ty, which is in this case going to be the adjacent side relative to the angle. So it'll be T times cosine of theta equals force of gravity, which is always good old mg. Now we do have mass, we do have little g, and then we can find the angle. So effectively we can get an expression for the tension with this equation right here. So for right now, I'll go ahead and just get an expression for tension that we can plug into our rightward formula over here, which is that tension is going to equal mass times acceleration due to gravity divided by cosine of this angle that we can find really at any time. Now that we have that, I'll go ahead and put a little asterisk here that's going to give us a portal back over to the x direction, because now we have a way to substitute something in that'll make this all solvable. So down here, I'm going to plug in for tension our little formula over here, which is mg divided by cosine theta times sine of theta. And all that, again, is going to equal Coulomb's law, which is just k times q squared over r squared. Now, sine divided by cosine is a trig identity. We can simplify that to tangent theta. That means that we only have to plug in our angle once, which is a little nice. So I'll go ahead and do that. And we'll say mg times tangent of theta is going to equal k q squared over r squared. Now at this point, let's go ahead and pause and see if we're actually able to solve for q at this point. Because if so, then I'd say you might as well go ahead and start rearranging and plugging in some numbers. So we do have m, we have little g, always. We can solve for theta at any point. We know k, it's Coulomb's constant, which is on your formula sheet. And then we know the distance between the balloons, which is r. So at that point, big Q is really our only unknown left. So we are in the clear. We can solve for big Q. So if you rearrange a bunch of this stuff to get Q on its own, ultimately you're left with Q squared equals mg times r squared times tangent theta, all divided by Coulomb's constant, k. Now if you square root both sides, really you're getting rid of the square on the Q over here, and so big Q must equal this formula right here. So we'll go ahead and plug in all of our values. So we've got the square root of our mass, which is 0.003 kilograms, times little g, which is always 9.8 meters per second squared. The separation distance r is 0.5 meters. Don't forget to square it. And then tangent, okay, we finally have to solve for the angle. So over here, we do have our triangle. It's one step. We just need to use inverse trig. So if we want to find an angle, and we have the opposite side and the hypotenuse, then we can find the angle very quickly by using inverse sine. So sine inverse of opposite over hypotenuse is going to be 0.25 divided by 1.5, which in your calculator should amount to about 9.6 degrees. So these balloons aren't separated by a whole lot, but they are deviating at least a little bit. So back over here, we're going to plug in tangent of 9.6 degrees, and then all of that junk on the numerator is divided by Coulomb's constant, k, which is 9 times 10 to the 9 units. I'm not going to bother. All right, so after all that, if you calculate all that, you square root it, you should end up with a charge on each balloon of 3.72 times 10 to the negative 7 coulombs. And if you want to simplify that a little further, generally it's good practice in electrostatics to denote something in units of microcoulombs, which is a really common, I guess, scale factor that you'll be seeing in this unit. Now, in this case, this would convert to about 0.372 microcoulombs, where micro is 1 times 10 to the negative 6 coulombs. So, just for the record, you can express it as that usually. All right, and so that's really the main part of this problem done. The last thing is a bit of a silly step, but we'll still do it, and it's to find the number of excess electrons that each balloon has. Now, keep in mind that this number right here that we got, the charge, is quite small. You're going to find that, conversely, the number of excess electrons on each balloon is quite large. So if you remember, the amount of charge on a singular electron is about 1.602 times 10 to the negative 19 coulombs per electron, ultimately. Very small amount of charge, but that's about as small as it gets. So what we really need to do is just take this amount of charge and divide that by how many coulombs per electron you have, because as dimensional analysis will show, that should get us in units of electrons, basically. So over here, we're going to write out our charge, which is 3.72 times 10 to the negative 7 coulombs. And then with dimensional analysis, on the top, we want Coulomb, or sorry, we want electrons. So we'll just do for 1 electron. On the bottom, we should have something in units of coulombs. That way we will get rid of the coulombs unit. So over here, for every 1 electron, you have 1.602 times 10 to the negative 19 coulombs. Very compacted here. Now I know that that should be a negative charge. Here, I guess it's kind of just assumed that these balloons must have a net negative charge if that's the excess charge that's given to these things. So we'll just go ahead and assume that that's the case. Now at this point, we're basically taking this number and dividing it by 1.602 times 10 to the negative 19. So if we do that, then you should find that the number of excess electrons amounts to 2.3 times 10 to the 12 electrons per balloon. That's a lot of electrons, but they are very small, so I guess that tracks. And that is your tabletop sized problem. The next 2 problems are going to be a bit more abstract, but I think you're also going to find they're a bit more direct in terms of how you apply Coulomb's law. So we'll take a look at those next. All right, now this next example is kind of nice by comparison. The calculations are going to be a bit simpler because you're not going to have to apply as much like crazy physics stuff. It's mostly just direct Coulomb's law. The problem with this problem is that it seems, at least on the surface, like it's going to be really tedious. So I'm going to show you some tricks that you can use to help save yourself some time on problems like this that feel like they're going to end up being very tedious. One thing to learn with electrostatics is that symmetry is your best friend. And here, because electrostatic force operates on that equal and opposite principle, you can use that to save yourself some time once you've gotten most of your main calculations out of the way. So, to start, we have 3 charges on a number line right here. Each tick mark represents 1 meter of separation distance. So some of these are quite far away from each other. And our goal is to find the magnitude and direction of the net force on each of these charges, 1, 2, and 3. So it seems like there's going to be a lot of forces that we're going to have to solve for here. So first, one thing to note is the units that are given here. These are given in MC, and here, the lowercase m implies milli, kind of like millimeters. So over here, I'm just going to note that 1 MC is 1 millicoulomb, which is equivalent to 1 times 10 to the negative 3 coulombs. Now, this is also going to be a problem where I show you my shorthand for scientific notation. This is something that I use for universal gravitation as well as electrostatics, because it gets really annoying having to write blah times 10 to the blah over and over and over again for these calculations. So if you recall from like a calculator, for instance, they usually denote scientific notation as something like 1e negative 3 or something. That's how I'm going to denote this whenever we're writing out the numbers over here. It just saves a little bit of time. It looks a little bit cleaner. I like it. Just don't confuse this with exponential e. With that in mind, let's go ahead and figure out what our directions are going to be. This goes back to that point of advice that I gave you on making sure you're drawing a free body diagram first. I promise it helps. So over here, first thing I'm going to do, just to help us organize a little bit better, is to color code these charges. That's just so I can color code the forces too and make things look a little prettier. So I'm going to make this charge red, this charge blue, and then this charge green over here. Now, keep in mind, again, that like red charge is not going to exert a red force on itself. This should only have a force on it due to these other 2 charges right here. So for instance, this first charge, Q1, is going to have a force acted on it by Q2 for sure. So over here, let's take a look at these 2 charges themselves. So Q1 is going to have a force acted on it by Q2 that is attractive, because both of these charges have opposite sign. It's going to be an attractive force. So over here, I'm going to denote that there is a blue force due to Q2 acting on Q1. And because it's a force from 2 on 1, I'm going to denote that by my naming convention as F21. So the force from 2 on 1. Now green is also going to exert a force on Q1. So over here, again, I'm going to draw a green force acting on charge 1. And because here, Q1 and Q3 are again of opposite sign, it is still going to be an attractive force. So the force, or Q3, is going to pull Q1 towards itself. So over here, again, I'm going to draw a force that points towards Q3 attractively. And here, again, I'm going to note it as the force from charge 3 on charge 1. So F31. Hopefully that makes sense. Otherwise, we'll get a feel for it on these other charges. So with that in mind, let's take a look at Q2 now. So over here, Q2 is first going to have a force acting on it due to Q1. So over here, I'm going to draw a red force. And again, Q1 and Q2 both have opposite sign. So Q1 is going to exert a force on Q2 that is attractive. So it's going to pull Q2 towards itself. So this force from 1 on 2 is going to be denoted as F from 1 on 2. Now green is going to exert a force that is repulsive, our first one of this problem. So Q3 and Q2 both have like sign, so they should repel each other. So Q3 is going to push Q2 away from itself. So Q3 will have a force like that, acting to the left. And we're going to denote that force as F from 3 on 2, F32. Finally, we have the things from Q3. So first, Q1 and Q3 have opposite signs, so it's going to be attractive. That means that Q1 is going to pull Q3 towards itself. So this force, which will be denoted as F13, will be acting to the left. Finally, Q2 and Q3 have like charge. They will be repelling each other. So Q2 is going to push Q3 away from itself. Therefore, Q2 is going to apply a rightward force on Q3. And because it's from 2 on 3, this will be called F23. Okay, bit of gymnastics there with direction and naming conventions and stuff, but taking or paying mind to doing that sort of thing up front is going to help a lot with organization when you start plugging in some numbers and worrying about direction. So finally, let's go ahead and start working out this problem. So first is Q1. And so here, the name of the game is to really just calculate these two forces and then add them together as vectors. So first, let's do F31. F31, so force of charge 3 on charge 1, is equal to Coulomb's constant times the absolute value of charge 1, which will be 1 times, well, let's just do absolute value of charge 1 for now, Q1, times the absolute value of Q3, because its charges 1 and 3. Then we're going to divide by the distance between 1 and 3 squared. Now here, again, I'm using the absolute value brackets because otherwise, if we start plugging in positives and negatives willy-nilly into this thing, you might accidentally confuse yourself with our usual convention for positive and negative, meaning right and left or indicating direction. I recommend you don't do that just so you don't confuse yourself, because that will not always work out the way you want it to. So down here, let's go ahead and plug in some numbers. The Coulomb's constant in my little abbreviated form over here is generally just 9e9. Nice and short, much easier than the alternative. The magnitude of the charge of Q1 is 1 times 10 to the negative 3, so 1e negative 3. And then the absolute value of charge 3 is 2e negative 3. Then we're going to divide by the distance between these two. Ooh boy. Okay, so if you count all the way from charge 1 to charge 3, it amounts to 30 tick marks, meaning it's going to be 30 meters. It seems like a large distance, but you'll find when these numbers evaluate that it really is a surprisingly high amount of force given that distance. This value evaluates to about 20 newtons of force between charges 1 and 3. And we already indicated up here that this force should be acting to the right. So I'm going to draw a little arrow indicating that that force is 20 newtons to the right. That is our first force done. Now we need to find the force from 2 on 1. So F21 is going to equal K, which is, well, just K, times charge 1, which is Q1, times the absolute value of charge 2, divided by the distance between 1 and 2 squared. Now again, plug in some numbers here. We've got 9e9 for Coulomb's constant, 1 times 10 to the negative 3, 1e negative 3 for Q1, and then we have 4e negative 3 for charge 2, and then we're dividing by the distance between these fellas, where here, the distance is about 10 tick marks, so it'll be 10 meters squared. If you evaluate that in your calculator, that'll amount to about 360 newtons. And again, this force is acting to the right, so we'll just draw a little right arrow to indicate direction. All right, nice and cool. So finally, we just need to find the net force on Q1. So down here, I'll just go ahead and indicate that we are finding the net force on charge 1, which is going to be 20 newtons to the right, or you could say positive 20 if you want, plus positive 360 newtons, or 360 newtons to the right, and that's going to equal 380 newtons to the right at the end of the day. So that is your net force on charge 1. And normally, if this weren't a tedious gymnastics problem, that would be the end of it. But we still got 2 other entire charges to find the net force for. So let's power through. So on Q2, we do have one new force, which is F32. Let's go ahead and find that one first. So the force from charge 3 on charge 2, again, is going to equal Coulomb's law, which is K times, in this case, absolute value of Q2 times absolute value of charge 3 divided by the distance between 2 and 3 squared. Now this force is acting to the left, so it's important to denote that. We have something a little different this time. So if you go ahead and plug those numbers in, we've got 9 times 10 to the 9. I feel like I'm going crazy. Times Q2, or absolute value, is 4e negative 3, and then Q3 is 2e negative 3, all divided by the distance between these fellas. Now this distance is going to be about 20 tick marks. You can find that through the difference between the other distances, because that's really all the space that's left. So down here, this is going to be 20 meters squared, and that force is going to evaluate to 180 newtons to the left. Cool beans. Now, I have some wonderful news for you all, with this example at least, which is that we have basically done all of the crazy calculation that we need to do in this problem. Again, thanks to the absolutely lovely equal and opposite principle. You see, the next force that we have here is the force from 1 on 2, or the force from charge 1 on charge 2. And so over here, we're going to go ahead and just write out that, that is the force we want. But before you actually go out and calculate that, keep in mind that the equation for this is effectively going to be the exact same calculation as the force from 2 on 1 over here. The reason being is that these charges are exerting equal and opposite forces on each other. The only difference is going to be direction. So here you can use the equal and opposite principle to say F12 is going to equal the same thing as F21. The only difference being direction. So just make them negatives of each other. So without having to do anything crazier, we can say that F12 is going to equal effectively 360 newtons, but it will be opposite in direction. So instead of acting to the right, it's going to act to the left. That's all you need to do. Nothing crazier. So with that, we've saved ourselves a lot of time and a lot of frustration. And so down here, we can go ahead and find the net force on Q2. So net force on 2 is going to equal 180 newtons to the left plus 360 newtons to the left, which is going to amount to 540 newtons to the left, or you could call that negative 540 newtons as well, if you're feeling a little brave with sign conventions. Okay, finally, last one, Q3. And again, we can use the ever lovely equal and opposite principle here to make really quick work of this guy. Watch. See, our first force is going to be F13. So we'll go ahead and write that first. So this is the force from charge 1 on charge 3. Now here, again, look for a force that involves those same 2 numbers and see if you've already calculated it. All the way over here, we calculated force from 3 on 1. So we have already technically done this calculation. So over here, we can say that F13 is going to equal the negative of F31. So again, they're equal and opposite forces. So this force, F13, is going to equal 20 newtons as a magnitude. It's going to be opposite in direction. So instead of going to the right, it's going to go to the left, like that. Cool. Then finally, we have F23, our final force. So over here, F23 is going to equal, let's see, where, there we go, F32. So there's our pair. It's going to equal the negative of F32. So again, this force is going to equal the same magnitude, so 180 newtons, but it's going to be opposite in direction. So instead of going to the left, it's going to be going to the right. And with that, we can find the net force on Q3. So net force on 3 is going to equal 20 newtons to the left plus 180 newtons to the right. Finally, some forces with opposite direction. And these forces, because they have opposite direction, we need to subtract them from each other. 180 is going to win that battle. So we will end up with 180 minus 20, which is 160 newtons to the right. You could also do that calculation as negative 20 plus 180, which would amount to positive 160 newtons indicating it's going to the right. Whatever the case, we just made a an otherwise very tedious problem, at least a little bit quicker, using that principle of equal and opposite forces. So one thing that's going to be really helpful with electrostatics in the future is just making use of symmetry and simplifications wherever you can. I recommend you take full advantage of that, because it'll save you some time and some frustration. You'll thank yourself later. Be kind to your future self. With that, there is one more example that I would like to cover. So let's get to it. All right, last example here, and we've started heading into 2 dimensions. So this is just going to show how that works in 2 dimensions. It's really no different from any other 2-dimensional vector problem. Ironically, we saved the shortest one for last, so this example shouldn't really take too long compared to the other 2, especially using all that we know now. The goal for this problem ultimately is to figure out the net force on Q0, which is this charge here that's placed at the origin on these axes. Our goal is to express the force as both components as well as in overall magnitude and direction. So we'll find the components first, then we'll use Pythagorean theorem and inverse tangent to get the magnitude and direction. And it's worth noting that each square or each line is 1 meter apart from each other. So the units here are going to be meters. All right, with that, again, first I'm going to do some color coding just to make things look a little bit nicer again. I'll make Q1 here red, and I'll make Q2 blue on the other side down here. I'm not going to worry about Q0 because we don't really care about the forces that it's exerting on the other charges here. Thank goodness. Okay, so first, I recommend drawing a free body diagram as always. So let's look at Q1 and Q0. These charges have opposite sign, so it's going to be an attractive force. So Q1 is going to try to pull Q0 towards itself, meaning that the force of 1 on naught, or F10, is going to be acting to the left. Now for Q2, these charges, Q0 and Q2, have the same sign, so it's going to be a repulsive force. So Q2 is going to try and push Q0 away from itself. So this force is going to be acting upwards. And because it's the force from 2 on naught, it's going to be F20 as its label. All right, that's basically a free body diagram. We are effectively done with that. So over here, let's go ahead and calculate our forces. So first, F10 or 10 is going to equal, of course, Coulomb's constant or Coulomb's law. So K times Q0 times Q1 divided by the distance between them, so R10 squared, is going to equal, again, our abbreviated Coulomb's constant, so 9 times 10 to the 9, times Q0, which is 1 times 10 to the 3, it's in millicoulombs, times 12 times 10 to the 3. Again, we don't really care about that negative sign. Don't worry about it. We've already considered it. And we're going to divide that by the distance between them. Here, it's 1 to 3 meters squared. Then we just need to multiply everything out. If you do that, you should find that shockingly, no pun intended, this electrostatic force is quite strong. It is 12,000 newtons to the left. And you might be thinking, whoa, these things are in millicoulombs. That's not a whole lot of charge. You're going to find very quickly in this unit that electrostatic force is incredibly strong compared to the usual stuff we're used to dealing with, like gravity. Keep in mind that Coulomb's constant is a pretty large modifier. It's, 9 billion basically. So charge is a pretty strong force out of the 4 fundamental forces in the universe. It's worth noting. All right, so now we're going to do F20. So over here, it's going to be K times Q0 times Q2 divided by the distance between them squared. So that'll just be R20 squared. And then same thing. So 9 times 10 to the 9 times our Q0 charge, which is 1e negative 3, times Q2, which is 16 millicoulombs, 16 times 10 to the negative 3. Then we're going to divide all of that by the distance between these squared. So 1, 2, 3, 4 meters squared. Evaluating this, the force between Q0 and Q2 is going to be about 9,000 newtons. And again, we denoted that this force is acting upwards, so I'll just go ahead and put an up arrow there, just for solidarity. All right, and so we've gotten our components. Now we really just need to do some trig stuff to get the magnitude and direction. Now over here, I'm going to go ahead and draw these vectors so we can visualize exactly where this net force is going to be pointing. If we've got a horizontal force due to Q1, and then a vertical force due to Q2, and those forces are adding as vectors, then tail to tip, we are ending up with a net force that's going to be going up and to the left like this. So this is our net force on Q naught. We also need to make sure that we're finding this angle. So I'm going to be finding that one relative to the negative x-axis. So over here, net force, the magnitude of it at least, on Q naught, is going to be good old Pythagorean theorem. So over here, we're just going to do the square root of one leg squared, 12,000, plus 9,000 squared. And if we evaluate that, you should amount to a magnitude of net force being 15,000 whopping newtons. That means if this thing is a, subatomic particle like a proton or an electron or something, it is zooming. Well, I guess it can't be a proton or electron here, but you get the idea. If it's a very small particle, this thing is going to be going fast. So we've got the magnitude here. So we just need to find the angle and we are done. So over here, angle, I'd say we have the components, so might as well use inverse tangent. So inverse tangent of opposite over adjacent is going to be the opposite side, 9,000, divided by the adjacent side, which is 12,000. Just going to amount to about 37 degrees above the negative x-axis. So usually I just like to draw a little thing like that to be extra sure. All right. And that's basically it. So hope I gave you a pretty good amalgam of ways to apply Coulomb's law here. We've got a tabletop example. We've got a really tedious example that makes use of symmetry to speed things up. And then finally, an example in 2 dimensions. And any 3 of these problems are pretty common examples of how you'll see and apply Coulomb's law in this class. So next time, we're going to be covering electric fields and some of their applications. So until then, thank you for watching, and I will catch you on the next one. Peace.